an der Universität in Göttingen zur 10. Jahrestagung der Neurowissenschaftlichen Gesellschaft. Und die Hertie Lecture dieses Jahr hält Professor Miguel Nicolelis von der Duke University. Sie haben bestimmt schon von ihm gehört, wenn Sie in den letzten paar Monaten, ja eher schon Jahren, die neurowissenschaftliche Berichterstattung auch nur ansatzweise verfolgt haben. Professor Nicolelis, it's nice to talk to you in person.
Oh, my pleasure. Thank you for the invitation.
Listening to you, reading your books, you must be the shining star of the transhumanists. Is it that you read too much science fiction, or it feels like the future is already here?
Well, I don't know. I don't think I'm not even part of the transhumanist movement. I'm just a neuroscientist. I did read a lot of science fiction, but I think what we are doing is not science fiction, is really neuroscience at the limit of what can be done right now, and actually probing interesting questions that, using this paradigm brain-machine interface that we pioneered at Duke University.
Let's start with Aurora. You taught an ape to use a third arm. How did you do that?
Aurora was the first rhesus monkey to actually perform a closed-loop control brain-machine interface. We have done these experiments a few years before Aurora with rats and owl monkeys, a monkey species that is from the New World, from the rainforest of South America. But Aurora was special because she not only were able to control a robotic arm to reach, but also to grab. And she was doing that playing a game on having a computer screen in front of her, so she had visual feedback, so she could see what she was doing. And in a given moment, the secret of all this, of course, was the ability to record at that time 100 cells from Aurora's brain simultaneously, the electrical signals that these 100 cells produced, and transform the motor coding or motor information that was embedded in those electrical signals into motor digital commands that the robot could actually take advantage of. But the key of the experiment was Aurora being able to see what was going on, because that altered the way her brain worked and interpret what she was doing. And that's the reason she was able to assimilate the robotic arm as part of her body representation. That's our theory, at least. So she was, yes, the first monkey to have a third arm, in addition to her two biological upper limbs.
That's the point, in addition to, so she could scratch or whatever while she was using her third arm?
Yes, after a few weeks of training with the brain-machine interface and using a robotic arm to play a game, we realized that she has never lost the ability to control her own body. So in effect, she was able to do a task with the robotic arm just by thinking, and also using, her two arms to do other things that a monkey does normally. So the brain somehow was able to incorporate that piece of machinery as a third upper limb in that monkey.
So it was the brain of Aurora learning and not the software or the computer?
Yeah, there were two types of learning there. For a while there was both the brain of Aurora and the software that was learning how to map her brain activity into movements that we could reproduce in a robotic arm. But in a given moment of the training, we stopped the learning of the machine. The machine basically learned as much as it could. But Aurora's brain, as our brain, continued to learn, continuously incorporating the new feedback and the new information that we're giving to her. So in essence, the whole experiment only worked for two main reasons. One, because we could record 100 cells simultaneously. And two, because of Aurora's brain plasticity, this property of adapting, that the brain has, the adult brain has, of adapting itself to the new contingencies and new contexts that you were facing in our daily lives.
You already mentioned the multi-electrodes. You had to develop those by your own, didn't you?
Yes, I started that in the mid-90s. I actually started as a postdoc doing this in the late 80s. But in the mid-90s, we started really producing new technology and new devices in our own lab at Duke University. And that is the secret also of the progression of these experiments, because now we can produce not only high-density, three-dimension sensors that allow 1,000 micro-wires to be implanted per cube, per sensor, and we can put many of those in a brain these days, but also get a wireless interface and that allows us to broadcast these thousands of signals from the brain without any cables or any wires. So this is all developed in-house and is allowing us to now dream about potential clinical applications in patients.
This is complex, but it gets more complex because you learn from a rat that the receptive field of a neuron has changes over time.
Yeah, I think all the basic research that we did in the late 80s and beginning of the 90s was vital for the emergence of this paradigm, brain-machine interface, both from a technological point of view, developing these electrodes, developing the software, analyzing, getting used to these huge data sets that nobody had seen before. But as you said, also the basic science discoveries were essential. Because when I was a postdoc, the first paper I published as a postdoc showed that the brain was much more dynamic and that the maps that we talk about in the brain were much more fluid, much more capable of changing as an animal does something or learns something. And in the question that you mentioned, the receptive fields, this was a classic property of neurons that for a long time people thought were only static. And we saw that that was not true, that these receptive fields were continuously changing. And actually they didn't mean much if you think about a neuron, because a neuron doesn't mean much for a brain. It's like trying to say that a star in the universe means anything for the whole dynamics of the universe. The only thing comparable to the universe that we know is the brain. And you know, you have 100 billion neurons in our heads, and that's comparable to the number of galaxies in the universe. So a neuron means very little. And this is very difficult for classic neuroscience, because we build a whole field centered on the single neuron doctrine. And so it has been quite a struggle to basically convince my colleagues that the goal is actually looking into populations of neurons rather than isolating single cells.
So motoric and sensoric maps in the brain are quite plastic, but accepting an artificial third limb, this has a philosophical dimension, doesn't it?
What we did in monkeys, just recently we are showing that we can extend this plasticity to territories that nobody actually thought possible. For instance, we just published a paper showing that rats can acquire a new sense. They can basically, through a prosthetic device, they can start touching what was otherwise invisible light, infrared light. You know, we mammals cannot see infrared light, and we cannot feel the temperature the infrared radiation produces. But we actually created a link between an infrared sensor and the touch cortex of these rats. And after 4 weeks of training, they were able to track sources of infrared in an infrared universe by touching the light, not by seeing the light. They couldn't see the light, but they could feel it as a sort of a tactile stimulation. And that's just the beginning. In other experiments, we have shown that perhaps our sense of self not only does not end at the end of our body surface, not only it incorporates the tools that we use in our daily routine as part of us, but it may even incorporate the people that we socialize often in our lives. Our sense of self may include our social acquaintances. And that's a concept that we are just starting to develop and trying to demonstrate that would basically throw this whole image of what is the body schema that the brain has, or the sense of self, wide open.
Amazing. You changed focus from motoric maps to sensoric maps, and you taught an animal to feel the surface of a simulation?
Basically, we first made these monkeys assume that an avatar body, a virtual rendition of a body in a virtual space was their body. So they learned to control first one hand and now two hands of an avatar and explore objects, virtual objects that we create by programming on a virtual environment. But they had to choose one out of three objects to grab to get a juice reward. That's how monkeys do all these games. They get a reward that motivates them to play the game. And they love to play video games like we do. And they like to win. That's the other thing. They're very ambitious, yes. And so what we did was they had to choose one out of three objects, but the three objects look alike. They were identical visually. So they would not be able, since the objects were changing position, there were three objects and they changed position. The correct one is always changing position. The only way to grab the correct object was to feel the texture that we created, a virtual texture that we created of each one of these objects. And the only way to do that was to rub your virtual hand on the surface of this object. And as the monkeys did that, we sent an electrical message that was proportional to the texture directly to the touch cortex of these monkeys. And in about 5 weeks, these monkeys learned to perform this tactile discrimination task as if they were using their own hands to do that, but they were using a virtual hand. So we established a bidirectional communication between the monkey's brain and the avatar hand and the brain without interference of the body, because neither the monkey's body was moving nor the skin of the monkey was receiving any feedback. The feedback was delivered directly into the brain.
Did you say it takes 5 weeks for the animal to learn a new sensoric system?
Since we cannot communicate with the monkeys, we cannot talk to them, we cannot tell them what they want, what we want them to do, or what they should do to get a reward, this has to be done step by step. You know, it's a very tedious process. In a human, I'm very confident that would be much faster, because we can instruct the patient. So if one day we use this technology to replace sensory information that was lost, let's say by a spinal cord injury, that makes people not only paralyzed below the injury, but also unable to feel the body below the injury. If we one day can use this technology to restore sensitivity of a body to this patient, I'm almost sure that this will be faster than what it took for the monkeys to learn.
Right now, everybody is talking about the brain-to-brain communication. What was the setup?
Yeah, basically, we started this project at the same time we started the infrared rat project. So we are always interested in trying to find the limits of plasticity. And first, when we added the infrared, we realized that we could add a new sense. So that was, very shocking by itself. But at the same time, I had this idea of, could we actually enhance the sense of self or the body representation in the rat brain or the monkey brain by actually incorporating another body into that representation? So could a rat just perform a task using information gathered by the sensory receptors or the sensors of another body that he doesn't even see or know the existence of? And that's when I designed in 2005 this brain-to-brain experiment. It was theoretical in the beginning, so we had to, I have in fact the first drawings that I made trying to put this to work. And it took a long time to get the setup to work because it's a very challenging paradigm. But essentially what we did was to have 2 rats now, and now we are working with 2 monkeys doing this similar thing. But the paper that just came out showed that 2 rats, one rat is called the encoder and the other is the decoder. Both have a general idea what they have to do, but the encoder is the only one who is actually doing the task that we ask animals to do. So there are 2 tasks that we did. So this first animal either uses its whiskers, facial hair, to probe the diameter of an aperture that is changing, and it can achieve 2 different diameters, a very narrow or a large diameter, or wide diameter. The first animal is putting the whiskers on the edges of these bars, and is calculating the diameter and telling us by behavior, by putting the nose either in the left or on the right of a hole that exists in the chamber, whether that is a narrow or a wide aperture. The moment the animal does that, its brain activity that is encoding the diameter is transmitted to a second rat that is not touching anything, but it has to give us also a behavior answer whether the aperture is narrow or wide. Again, he's not using its own whiskers, the decoder. He's relying on information that came from the first animal. And we saw that in about 65 to 70% of the time, the second rat gives us the correct answer based on this transmission of a brain-to-brain signal. A second task uses a visual motor behavior. So the animal gets the first one, the encoder, gets a visual cue. And that visual cue tells the animal whether he has to press a left versus a right bar for a reward. So as the animal makes the decision, its brain pattern is transmitted to the second animal. And the second animal goes there and press either left or right according to what the first animal brain pattern tells him to do. Again, 70% of the chance, which is pretty high, this guy gets it right without receiving any visual cue. The interesting thing that makes the preparation even more interesting is that according to the performance of the decoder, we decide what reward the encoder gets. So if the decoder gets an error, if it doesn't get it right, the encoder doesn't get a bonus reward that it's expecting after it did it right. So it doesn't like that because it wants an extra reward. So what we notice is that following an error by the decoder, the encoder not getting the reward produces an effect that is the encoder improves the way it does the behavior, it makes it smoother, and the brain signal that it produces is clear, making it easier for the next try for the decoder to get it right. So that's how we saw the emergence of an interaction between this pair of animals that are not even seeing each other.
It is in one way still science fiction because Aurora was 2004?
2002.
2002. So we still don't have an adaptation for humans. Where are the problems in translating one into the other animal? Yeah,
there is a lot of issues. In fact, some people rushed to human applications soon after Aurora came out. After we published this paper in the United States, a couple companies were formed, and they tried to rush this as the usual, and it didn't work very well because the technology was not there. We have, patiently developed this over 20 years, because we wanted to find, for instance, sensors that you can implant in the brain that can last for decades. And we are almost getting there now because our monkeys, we have already, in one species of monkey, our monkeys, we have reached close to 7 years of chronic recordings. And the cells are there and the recordings are viable. In rhesus monkey, we are already getting close to 5 years of animals that we monitor continuously over this period. So we are very confident that we have reached now a level that can be translated to humans. But that takes time. It doesn't. If the motivation is to rush just because some company wants to make some money, that doesn't happen. And unfortunately in the US, usually that's what happens. Some people want to skip steps, and even though they got a lot of notoriety for some of those first trials, they never moved from there because the technology was not capable of doing any benefit, real benefit for patients. Because when you move to humans, you have to be sure that the benefits way outweigh the cost, because you're talking about an implantation of something inside the brain. So it has to be something that really gives a clinical benefit of magnitude. And that's what we have been waiting for almost a decade. And I think we are close to this possibility. We're close to the possibility of starting translating this to what we call prosthetic devices, neuroprosthetic devices that will really give gains, significant gains to patients that suffer from severe paralysis. Yeah.
With humans, there are some ethical issues as well. Not about what some communicators say, enslaving other people, that's quite science fiction, but there are possibilities to use your science in a military way. And one says you receive funding from DARPA.
Yeah, this is important to clarify because there was a mistake in the press. I think an article from the Reuters talked about this work was funded by DARPA. It was not. This work was all funded by the National Institute of Health and the United States, the branch of the federal government that works on biomedical research or funds biomedical research. 10 years ago, I had a grant from DARPA that ended, and this was focused on rehabilitation of veterans. That's how a brain-machine interface field got a lot of investments, but that was in the beginning, 2002 to 2007. There are other groups being funded by DARPA, but our laboratory is not funded by it. So we have no interest and no work being developed with applications like military applications. Our goal is rehabilitation medicine and proposing new ways of doing computing using, what we learned from neuroscience. But all this work is focused on biomedical research.
So no money from DARPA and no money from Apple?
No money from Apple, no money from Google, no money from any corporation so far, and no money from the military. Now, our lab is funded just by private foundations and the federal government in the United States focusing on biomedical research.
Okay, back to research. Those multi-electrodes are a huge challenge. and they are needed for the brain activity map and for the human brain project both as well. Where do you think are those multi-electrodes 5 years from now?
Well, we just recently crossed this boundary of recording about 2,000 neurons simultaneously in a rhesus monkey. So that's the highest number of neurons ever recorded. But we think that we are not at the limit yet. I think in the next 5 years we could get close to 20,000, and if we are, a little bit of help, we could get around 50,000. Because we have the technology now, we know how to get there. It's really a question of investment and being able to develop the wireless interface that for us now is about 1,000 channels, 1,000 to 2,000, to that level, to get 50,000 channels simultaneously. But with 50,000 channels simultaneously, you could, in principle, control a whole body exoskeleton, a robotic vest, with brain signals from the brain of a paralyzed patient. A severely paralyzed patient, a quadriplegic patient. So that's our goal. We are going to start with lower limbs as we translate this technology for humans. We're going to start with locomotion, getting someone out of a wheelchair, and then move up to the rest of the body as we progress in terms of increasing the number of neurons that we can record simultaneously.
Being kind of a futurist yourself, what do you think about those projects, the brain activity map and the human brain project?
The US, I cannot say much because nobody knows anything. There's just an announcement. It's the first time in my career, I have been in the United States for 25 years now. It's the first time a program is announced without us knowing what the program is and what is behind the program and who really is deciding what is going to come. So I cannot really comment on it. I hope that part of this program will be a push for the kind of technology that we have developed, to record large numbers of neurons in behaving animals and eventually in humans. The European project, I'm very critical of it because I really don't believe that the brain can be simulated. Not even a rodent brain can be simulated in a computer. There's a fundamental difference between, as my good friend Professor Ronald Sicurel likes to say, there's a profound difference between a mechanism and an organism. A mechanism, like a computer, is built by someone. There is a blueprint, there is step-by-step building. That's computable. You can simulate that in a computer. Any process that is engineered can be simulated. A brain or organism evolves. Nobody builds that. And the set of steps that make an evolution of this device become what our brain is not passable to simulation. You cannot simulate that in a computer because this is almost a pseudo-random walk. It's a sequence of random steps that took us from the trees to what we are right now. So our brains are, I like to say, and I said in my book, is copyright protected. We simply cannot simulate it into a computer because it's not computable. There's no single algorithm that can reproduce our human nature. So it's almost paradoxical that someone that interfaces brains with machines advocates this position, but I'm pretty secure, and with a few of my colleagues also, pretty secure that if the main goal of this project is to simulate a mammalian brain and claim that you can reproduce human nature in a computer or behaviors, that we consider part of human nature, is not going to work. It can be very useful for other things. It can take all this money and do a lot of good neuroscience research that is credible. But in the way it was sold, I'm afraid it's not going to happen.
Last question. What is your next goal?
Well, there are many, but right now we are concentrating on trying to get a public demonstration of this idea of an exoskeleton controlled by biological signals. So we have been working with a consortium, a non-profit consortium with European, American and Brazilian scientists for the last 3 years, and now after we received support from the Brazilian government, the federal government of Brazil, we are actually going to try to build the first exoskeleton, a lower leg exoskeleton controlled by biological signals originated in the brain, and see if we can have a short demonstration of this technology, a symbolic, emblematic demonstration in the opening ceremony of the Brazilian World Cup in 2014, the FIFA World Cup in Brazil, on June 12, 2014. We are hoping that if everything works, a Brazilian paraplegic will be in charge of the opening kick of the World Cup and walk autonomously from the edge of the pitch to the center field, and there, controlling this exoskeleton, be in charge of the opening kick of the World Cup, to show to the entire world in a major sports event that science, this kind of science, can have a major impact in our society, since there are millions of people worldwide that depend on wheelchairs or other ways to locomote. That really, if there's a political decision of investing intelligence and money on this, that we could make these wheelchairs obsolete in a generation.
Maybe this is the real ethical problem. You will kill football as we know it 15 years from now.
Oh no, I don't think the Brazilian style. I don't think will be killed, but it may help some other teams to get close to us.
Okay, thank you, Professor Nicolelis.